Previously, we learned how to describe uniformly accelerated rotational motion and how to connect the rotational world to the linear world. But there's one very important thing that we haven't covered yet: forces in the rotational world. In the linear world, acceleration is caused by a given force, but in the rotational world, angular acceleration is caused by a torque, the rotational equivalent of force. We're going to go through the concept of torque in this tutorial and then move on to momentum in the rotational world. We've learnt about linear momentum and collisions in the past. Now we're going to learn about angular momentum and how it is conserved, another fundamental principle upon which all physics is based. Let's start with a discussion of torque. So let's say you wanted to loosen a nut by rotating it with a wrench. Is it easier to use the wrench when you apply your force closer to the nut or farther away down the handle of the wrench? Similarly, let's look at a door on a hinge. Is it easier to push a door closer to the hinge or farther away from the hinge? You probably guessed it, but it's way easier to apply a force farther away from the axis of rotation. This clearly means that the force required to cause a rotation decreases as the distance from the axis of rotation increases. Therefore, it's useful to define a quantity called the torque. So we call this torque tau, and this takes into account the magnitude of the force and the distance from the axis of rotation. But what exactly is torque? We define torque as a measure of force that can cause an object to rotate about an axis. Remember, this means that torque is a vector quantity, so that means we need to care about the direction of force on the axis. So just as a reminder, the torque is a vector with a magnitude and a direction. So then, in order to continue with our analysis of torque, let's look closely at our example of pushing a door. So, using a top view, we can draw an example of a door with a hinge on one side. So here's our door, and let's say this is the hinge that it's going to swing on. So we're going to call this the axis. And we're also going to push the door on the right side and use this as the applied force. So let's use red to represent the applied push. So this is the applied force. Something else that we need to remember is that this applied force happens a certain distance away from the axis of rotation, and we call this distance r, which is also a vector. Just keep in mind, r represents the distance away from the axis of rotation that you're applying the force, but also we call this r because usually it has to do with the radius of the rotational path. So if I were to push this door, then that means that the path the door would take would be a circle. something like this. And we'll call this the path of a full rotation. So in the case of circular motion around an axis of rotation, your distance r is simply the radius. So that means we can define torque using an equation, and we can say that the torque is going to be tau equals to r times F. And we note that the torque is going to increase with both the force and the distance. But there's also something else to keep in mind here. No matter what, we are looking at an axis of rotation, which means that there's an imaginary circle of radius r that our contact point is on. So we've drawn our circular path. From this diagram, we can see that the applied force here is tangential to a circle of radius r. So something I want to add here is that the applied force is tangential to the circular path. And right now, it's very important to say that only the tangential component of a force will cause a torque. But it makes sense, right? If we push on the edge of the door, for example, in green, if I were to push on the door this way, then I wouldn't really be moving the door. I'd be pushing onto the hinge. So if we push on the edge of the door, our tangential component is 0, so we'd never cause the door to swing. So with this knowledge, we need to generalize our equation for torque, just in case there's an applied force that might not be tangential to our circle. And in order to proceed with this, we need to draw another diagram. So let's go ahead and do that as well. Let's draw an object, and then somewhere off to the side, let's draw a dot to represent the axis of rotation. So we're going to generalize our door. So here is another example. So we want to call this a generalized diagram of torque. So we've drawn an object here, and we want it to rotate around some sort of axis. So let's use a black dot to represent the axis of rotation. So we have this. This means that the object is going to rotate around this axis, so we can trace out the circular path that it should experience, like this. From this, we can now label the distance the object is away from the axis. From the diagram, we can see that this distance is simply just the radius. So we have this as r. We can also draw some sort of applied force acting on the object at some angle theta from the radius or vector r. So let's use red to represent the applied force, and let's not make it 90 degrees or tangential. Let's just draw some sort of applied force that's off to the side over here and label it as F. And that means it's going to be at some sort of angle theta from the vector r. So from this, we now have to do some further analysis. We know that only the tangential component of a force causes a torque? So we'll have to approach this in one of two ways. Number one, we can find the tangential component of force, which is the value of force that's perpendicular to R, or we can find the component of R that is perpendicular to the force, and that is called the moment arm. So we'll go through both of these. With our diagram, first thing is being able to find this. So that is the tangential component of force, which is sine of theta is opposite over hypotenuse. So that means this is equal to F sine theta. And we'll call this equation 1. The other option was to get the component of R that's perpendicular to F. So if we wanted that, we would extend we would extend the force vector and we simply want to solve for this. This would be the component of R that is perpendicular to F, and we call this R sine theta. We'll call this equation 2, and this is also called the moment arm. So now, from our diagram, we can see that there's two generalized ways of representing torque. We can say from 1 that the torque is equal to R times F sine theta, which is simply RF sine theta. And from our second definition, we can say tau, or torque, is equal to the component of R that is perpendicular to the force times force, and that's also equal to RF sine theta. So that means we have a generalized definition of torque, and that is tau is equal to RF sine theta, which is basically the cross product of the two vectors. So this is an important equation to remember moving forward. Now, when we talked about forces back in the linear world, we also talked about work and power. So we do have to talk a little bit about work and power. Similarly, we can look at rotational work and power. And to calculate work, it's very similar. Remember, work was equal to force times displacement, so F times delta x, but using one of our conversion equations, we can represent delta x in the rotational world by multiplying it by r delta theta. So that gives us the connection to the rotational world. So then we have W equals to F r delta theta. We can represent this as RF delta theta simply just by switching these two around. But this is also tau. So this is tau, or torque, times delta theta. So this means that the rotational work done by torque is going to be given by what we've just derived. So we can say here the rotational work done by torque is going to be W equals to tau times delta theta. But there's also something else that we've covered before, and it's the work energy theorem. So just as an explanation, we know that work is equal to a change in kinetic energy, and it's the exact same in the rotational world, except now work is going to be equal to a change in rotational kinetic energy. So we can say W is equal to tau delta theta, and W is equal to delta KE, just like before. So now we can define rotational power. So rotational power, well, let's just first set this as the work energy theorem. Power has the same definition as before. It's equal to the amount of work divided by the time it takes to do that work. We know that work is equal to tau delta theta, so we can say, we can rewrite it like this. The other thing is to look at just this area, or this part of the expression. Delta theta is displacement, and delta t is time. So displacement over time is equal to velocity, but in this case we have angular velocity. So we have but omega is equal to delta theta over delta t. So our definition of rotational power is given by P equals to torque times omega. So just to summarize, and to scroll back, these are the main equations related to torque as well as work and power in the rotational world. In the linear world, when we were talking about forces and mass, we used Newton's second law to find a connection with acceleration. Remember, the net force was equal to mass times acceleration in the linear world. But in the rotational world, can't we have something similar? We do have the rotational equivalent of force being torque, and the rotational equivalent of mass being the moment of inertia. And if we apply Newton's second law, we should be able to relate to angular acceleration in the rotational world. So just as a recap, we have certain quantities in the linear world that we want to relate to the rotational world. So we have force, or net force, and in the rotational world we have the net torque, we have mass in the linear world, and we have moment of inertia in the rotational world. We have A for acceleration, and we have alpha for angular acceleration. So we already have F net equals to ma. In the linear world, and we need some sort of connection to the rotational world. So maybe we can just use one of the conversion equations we used before to connect angular and linear acceleration. Specifically, this one. So we can say, but A linear acceleration was equal to r times alpha. So we now have a new equation for F net is equal to mr times alpha. So if we were to solve for alpha, we would get F net over mr. But this expression isn't really helpful because we still have our force and we still have our mass in the linear representations. So how else can we relate this to values we already know? Since we are relating the linear and rotational worlds with tangential linear acceleration and angular acceleration, we know that the net torque is going to be equal to R times F net for a tangential force, since sine of theta is equal to sine of 90, which is equal to 1. We also know that I is equal to mr squared. So mr squared, and that's for a hoop or cylindrical shell. So this is when an object rotates about an axis. So now it looks like if we had an additional value of r on the top and bottom of this expression, we'd be able to rewrite alpha as something else. So we can multiply our equation for alpha by r over r, and we get alpha equals to r F net over mr squared. And isn't rf net just the net torque? And isn't mr squared just the moment of inertia? So therefore, we can say the net torque is going to be equal to I times acceleration. And now we have Newton's second law in the rotational world. So let's highlight this and call this Newton's second law. So just like in the linear world, we have to remember that in our rotational world, when we're looking at Newton's second law, we're looking at the net torque instead of just one torque alone. So we're going to go through some practice problems to help solidify these concepts. So let's go through a practice problem. When a ceiling fan rotating with an angular speed of 2.75 radians per second is turned off, a frictional torque of 0.120 Newton meters slows it to a stop in 22.5 seconds. What is the moment of inertia of the fan? So before we start, let's make a plan. We're given the initial and final angular speeds. So a ceiling fan rotates at an angular speed and it's turned off. So that would be its initial speed. So omega I, it's turned off, and a frictional torque is going to slow it down to a stop, which means that the final angular speed is going to be 0. We're also told that there is a frictional torque and nothing else is acting on the fan. This will allow us to calculate the net torque. So from this, only force acting on the fan. So we should be able to apply Newton's second law for angular acceleration. So we should be able to use tau is equal to I times alpha to figure out what I, the moment of inertia, is. So let's start with our first step. Essentially, it's just state known values and solve. So this is simple. We don't really need a picture for this one. We just need to state what values we're given, figure out what we're trying to find. So we know we need to use this equation. Net torque is equal to moment of inertia times alpha, and we want to solve for I. So we want to solve for I, which means we would need a value for the net torque divided by angular acceleration. So we need to find values for these two. To find the net torque, we know that only a frictional torque is acting on the system in the direct opposite of its motion. So that means the net torque is going to be a negative torque from friction on the system, and therefore it's equal to negative 0.120 Newton meters. Or tau F is equal to 0.120 Newton meters. Next, we want to be able to figure out our angular acceleration. So we want to find the angular acceleration. We're given omega I is equal to 2.75 and omega F is equal to 0, and we know that it stops in 22.5 seconds, so t is equal to 22.5. This seems like a rotational kinematics question, so we already have 1, 2, 3 values. We're trying to look for angular acceleration. So the one equation that gives this to us is omega F is equal to omega I plus alpha t, and we simply solve for alpha. So omega F minus omega I divided by t. We know that omega F is 0, so we end up with negative omega I over t, which is negative 2.75 over 22.5 seconds. We punch this into the calculator and we get negative 0.122, and this is in units of radians per second squared. So I now have my angular acceleration, and be careful here, we do need the net torque, so we're not looking for the value of frictional torque. We have net torque is equal to negative 0.120 Newton meters. Now we just plug this into our equation for I, and we have negative 0.120 divided by negative 0.122, and we get I is equal to 0.982 kilogram meter squared. So therefore, the moment of inertia of the ceiling fan is 0.982 kilogram meter squared. Here's another question. You're holding your outstretched arm at rest in a horizontal position. The mass of your arm is m, and its length is 0.740 meters. When you release your arm, it drops freely and begins to rotate about your shoulder joint. Assume that your arm is similar to the shape of a long, uniform rod. Find these two things: A, the initial angular acceleration of the arm, and B, the initial linear acceleration of your hand. So, let's first make a plan. We're looking at an arm that's essentially a uniform rod. We are told that the axis of rotation is the shoulder joint, and that the length of the arm is 0.74 meters. The first question asks for the initial angular acceleration of the arm. To find that, we should be able to use Newton's second law, tau is equal to I alpha, but this means we need torque and moment of inertia. Since the question specifically states that the arm is a long uniform rod, we can use the equation for moment of inertia for a long rod rotating about one of its ends. So that's actually I equals to 1 over 3 ml squared, where L is the length of the rod. The torque will be the force acting on the arm that is perpendicular to its length, so that would just be the force of gravity, or mg. But remember, the force of gravity acts on the center of mass of the arm, and since the arm is uniformly dense, it's right in the middle of the arm, or at a value of 1/2 of L. After that, we can use a conversion equation to convert to linear acceleration. So, first of all, we do need to draw a diagram just so we can understand everything that's happening in this problem. So, step number 1. We want to draw a diagram and state our known values. So let's first draw our arm, which specifically is a uniform rod of length L. So that's our arm. And it is a length of L. The other thing we know is that the axis of rotation is at the shoulder joint, so we'll assume that the shoulder joint is right here, and we'll call this the axis. And we might as well label this as the shoulder joint. Another thing I've forgotten to add is the mass of the arm, so let's label this as M, as the mass of the arm. There's going to be a force of gravity acting on this arm when it's completely outstretched. So remember, the center of mass is where this force is going to act. So this is XCM. And we have a force of mg acting on the center of mass of the arm. Next, when we're looking at any angular motion of the arm, we're going to be looking at the hand on the far right that drops down and has a motion like this. This means we can model this as an angular movement and have angular acceleration going this way. So let's write down what we're given. We know that L is equal to, let's give us more space. L is equal to 0.740 meters. M is simply M. We know that Fg is equal to mg, and we know that g is equal to 9.8 meters per second squared. Next, we should indicate our coordinate system. Let's consider this clockwise motion to be positive, and let's consider down to be positive since there's no upwards motion. So we now have our diagram. We might want to try and apply Newton's second law. So step 2. We want to apply it to try and find the angular acceleration. So, we're looking for alpha, and we know that Newton's second law is the net torque being equal to the moment of inertia times alpha. So alpha is going to be equal to torque over moment of inertia. We know that the only force acting on this is going to be due to gravity, so we're going to have some sort of torque due to the force of gravity in the direction of rotation. And we know that we need the moment of inertia of a rod. So just remember, the arm has the shape of a long uniform rod, so I of rod is equal to 1/3 ml squared. So now we know that the equation for torque is the distance the force is being applied times the force itself. So RFG divided by 1/3 ml squared. So alpha is equal to R. We now need to figure out what R is, and that's the distance the force is acting on the system. We know that XCM is equal to 1/2 of the length of the arm. So we know that alpha is equal to 1/2 L times mg for your FG over 1/3 ml squared. The m's cancel out, which is why they didn't give a value for m. And that gives us 3/2 G over L. So alpha is equal to 3 times 9.8 divided by 2 times the length of the arm, which is 0.740 meters. Alpha is equal to 19.865 radians per second squared. Okay, so that answers part A, the initial angular acceleration of the arm. We want to now figure out part B, the initial linear acceleration of your hand. So let's first say this is part A answered. We now want part B, so step 3. We want to convert to linear acceleration. So to convert to linear acceleration, we just use the conversion equation from the rotational to linear worlds. We just use A equals to R times alpha. So the R here now represents the distance the hand is away from the axis of rotation. So it's very important to know that R might change depending on what you're looking at. So here we're looking at the hand. It's now at a length of L from the shoulder joint. So that means R is equal to L, and we can say A is equal to L times alpha, which is equal to 0.740 times the alpha we calculated, which is 19.865. And acceleration is going to be equal to 14.7 meters per second squared. And now you've answered part B as well. This question states that a fish takes some sort of bait and pulls on the line with a force of 2.2 newtons. The fishing reel, which rotates without friction, is a cylinder of radius 0.055 meters and a mass of 0.99 kilograms. A. What is the angular acceleration of the fishing reel? And B. How much line does the fish pull from the reel in 0.25 seconds? So, let's first make a plan. This problem involves two main components of a fishing rod: the reel that turns and the line that is wrapped around the reel and extends along the rod. So our focus is going to be the area around the reel that turns, since we want to know its angular acceleration and also how much line the fish is going to pull from the reel. But before we even do anything, we should figure out how the line and the reel are positioned with each other. If you pull on the line, the reel is going to rotate. Right at the point where the line leaves the reel, we can assume that the line is going to look tangential to the edge of the reel. Meaning if we take the radius of the reel as the direct line from the axis of rotation to where the line is going to leave the reel, we have a 90-degree relationship between the distance vector r and the line. We can now draw this and go from there. So step number 1, we draw a diagram and we state our known values. So the first step is to draw the fishing reel. So want to draw this a little bit larger. We have our fishing reel and the axis of rotation. We also have some sort of line that's wrapped around this reel. So we can assume it's wrapped tightly around the reel, and at some point it's going to exit. So this is the fishing line. And it goes up along the rod. We know that there's some sort of tension from the fishing line, and we know that if we draw the distance vector here and call this r, it is a direct right angle to our tension force or tension vector. So apart from this, there's a few other things. We know that the mass of the reel is 0.99 kilograms. We also know that this is a solid wheel. So that means if we are to calculate the moment of inertia, the moment of inertia of a solid disk is equal to 1/2 mr squared. Next, we know that the reel is probably rotating in this direction at some sort of angular speed. And because of this, we're going to get more and more of the fishing line out this way. So that means that we want to figure out in part B what happens in 0.25 seconds. So in 0.25 seconds, maybe your wheel has turned a displacement of theta, which also means that you would have unwrapped a specific delta x length of fishing line. So we have to be able to relate delta x back to delta theta. So delta x is equal to r delta theta, one of our conversion equations. What else are we given? We're given the value of r being 0.055 meters, and we're given the magnitude of the tension, which is 2.2 newtons. The next step is to apply Newton's second law to find angular acceleration so that we can answer part A. So we've drawn our diagram. Step number 2, we want to apply Newton's second law and find angular acceleration. So we know that there's a force involved when the fish pulls on the line and causes a rotation. This can be represented by the tension on the fishing line pulling away from the reel. So the net force acting on the reel is simply just T. So we have the net torque being equal to Rf sine theta, where theta in this case is the angle between the vectors r and f. We do know that f is just t, and we have a sine of 90 degrees. So that means we just have RT times 1. So in order to apply Newton's second law, we also need the moment of inertia I. So we know I is equal to 1/2 mr squared. So that means we can now have an equation for Newton's second law. Tau net is equal to I times alpha. We want to solve for alpha, so that's tau net divided by I is equal to RT divided by 1/2 mr squared. We can move the 2 to the top. We can get rid of an r in the top and bottom, so we have 2t over mr, which is equal to 2 times the tension, which is 2.2, divided by the mass, which is 0.99, and the radius, which is 0.055. So alpha is equal to 80.81 radians per second squared. So that answers part A. The next thing we want to answer is how much line does the fish pull from the reel in 0.25 seconds? So what we really want to find is delta theta so that we can find delta x. So step number 3 involves determining the displacement. So we want to know how much of the line was pulled from the rod. It means we should determine the angular displacement delta theta of the reel and then convert that to delta x using our conversion equation. So we're also given a time of 0.25 seconds. So this seems like a rotational kinematics question. We already have t being equal to 0.25 seconds. We're trying to find delta theta. We already know the angular acceleration, which is 80.81, which we just solved for. And we also know that the initial speed of the reel is probably going to be 0 because the fish is pulling it. So omega naught, or omega I for initial, is 0 radians per second. Okay, so I have 1, 2, 3 known values, which means I can solve for my fourth one. I just need to pick the correct kinematics equation. So we have delta theta being equal to omega it plus 1/2 alpha t squared. We know that omega I is going to be 0. So delta theta is simply 1/2 alpha t squared. We have 80.81, 0.25 squared. Delta theta is therefore equal to 2.525 radians. But we're not done yet, because we want to find out how much line the fish pulls from the reel. So we really need to find delta x. So we know delta x is equal to r times delta theta. R is simply 0.055, and we just found out delta theta was 2.525. So delta x is equal to 0.139 meters. And that answers part B. In this problem, a 0.31 kilogram cart on a horizontal air track is attached to a string. The string passes over a disc-shaped pulley of mass 0.080 kilograms and a radius 0.012 meters, and it's pulled vertically downwards with a constant force of 1.1 newtons. Find A, the tension in the string between the pulley and the cart, and B, the acceleration of the cart. So this is a rotational dynamics problem. This means we're not just looking at one object, but rather an entire system and putting everything we've learned together. So it's a little bit more complicated. It means we're going to need to draw a diagram to understand the question, and then draw free body diagrams to determine the relevant forces acting on each object. Then we can start to figure out how we can solve for what's asked. So we need to draw a diagram. And state our known values. So we should draw any free body diagrams here too, and remember to put in a coordinate system whenever necessary. So we'll do a general overview of the problem. We first have some sort of air track that's probably resting on a table. So we'll call this the air track. And we have some sort of pulley with an axis of rotation here, and that pulley has a mass m. We'll call this little m just to be easy. We also have some sort of cart, which we'll say it has a mass of capital M. And there is a string like this. Something else that's important is the fact that we're pulling on this string and making the cart move. So we'll draw a hand. It's an ugly hand, but it'll do. When we're looking at just the pulley, it's experiencing tension from two parts. It's experiencing tension from the hand pulling at it. It's also experiencing tension, which we'll label tension 2, coming from the cart. So because the tension in between the pulley and the cart is along the same piece of string, both these magnitudes are going to be the same, pointing towards each other for each mass separately. We also know that the mass is probably going to accelerate this way because we're pulling at the string. The known values that we have are little m, mass of the pulley being equal to 0.080 kilograms. We know that the mass of the cart is 0.31 kilograms. We know that the radius of the pulley is 0.012 meters, and we know that the tension that we're pulling with is 1.1 newtons. So now let's draw some free body diagrams. For each of our masses, we have the pulley, and we have the cart. So with the pulley, we have our vector r. We also have acceleration, angular acceleration going this way, and we'll assume that the counterclockwise direction is positive. We also know that the pulley experiences Ti going this way and another tension T2 going this way. Next, looking at the cart, we have the mass of the cart. We do know that there is the force of gravity acting on the cart and a normal force, but they're supposed to cancel out because the air track is a frictionless surface. So the only force that we should care about is the force of tension pointing this way. So now the only thing left is to draw a coordinate system. Let's say we have our x and y directions. And now we want to find out T2. So just by looking at these free body diagrams, it seems like I'm going to be able to come up with one Newton's second law equation for the pulley and another Newton's second law equation for the cart. One's going to be rotational and the other one's going to be linear. So I can say this is probably rotational, Newton's second law, and this is probably linear, Newton's second law. So I should be able to come up with the two equations and then be able to solve for T2. So step 2, we're going to determine the equations for Newton's second law. So just going to scroll down a little bit more. So we have two objects we need to look at, the pulley and the cart. Let's start with the pulley. We need to use the rotational version of Newton's second law. So we have pulley, and we have the net torque being equal to I times alpha. So if we're looking at the coordinate system, counterclockwise is positive, so that means we're going to have your torque coming from tension 1 minus your torque coming from tension 2 is equal to I times alpha. Remember, torque is equal to R times the linear force, so that means we have RT1 minus RT2 is equal to I alpha. And because we have a solid disk as our pulley, the moment of inertia is going to be 1/2 mr squared. We also know that acceleration A is equal to R times alpha. So we can plug these values in. Let's first factor out the R to get T1 minus T2 is equal to 1/2 mr squared. Alpha is equal to A over R. This means I can get rid of one R and then another R, and I get Ti minus T2 equals to 1/2 MA. T2 is equal to T1 minus 1/2 MA. And we're going to call this equation 1. Now let's take a look at the cart. So with the cart, we have F net is equal to mass times acceleration. The net force acting on this is in the opposite direction of our positive coordinate system. So we have minus T2, and it's equal to the mass, which is capital M, times acceleration. But keep in mind, acceleration is in the negative direction for us, so we must have negative A. So essentially, your negatives do cancel, and you have A is equal to T2 over M. And we'll call this equation 2. So we don't have acceleration, so that means we want to use equation 2 and plug it in to equation 1. And now we can solve for T2. Scroll down. T2 is equal to T1 minus 1/2 M. T2 over capital M. We have T2 is equal to T1 minus T2M over 2 capital M. That means T2 plus T2M over 2M equals 2 T1. We can factor out a T2 and get 1 plus M over 2 capital M equals T1, and we have T2 is equal to T1 over 1 plus M over 2 capital M. So let's just solve for T2. That's going to be the tension, the first tension, which is 1.1. Then we have 1 plus the mass of the pulley divided by the mass 2 times the mass of the cart. And T2 is equal to 0.974 newtons. So that answers part A. Now we want to answer part B. And part B requires us to find the acceleration of the cart. So step 3. Find the acceleration of the cart. We know that equation 2 has A equals to T2 over M. All we have to do is just plug in the value we got for T2, which is 0.974, divided by the mass of the cart, which is 0.31, and we get A equals to 3.14 meters per second squared. And this answers part B. In this question, you pull downward with a force of 28 newtons on a rope that passes over a disc-shaped pulley of mass 1.2 kilograms and radius 0.075 meters. The other end of the rope is attached to a 0.67 kilogram mass. We want to find the tension in the rope on both sides of the pulley. So, this is a question related to rotational dynamics. We need to draw a diagram of the situation and then create free body diagrams for each mass involved. We already know that there's a pulley in the middle. On the side where we're pulling, there's a downwards force of 28 newtons on the rope, which is basically the tension the rope experiences on our side of things. Let's call this T1. But what about T2? We need to consider the pulley and then transfer the knowledge we learn to the hanging mass. So let's start by drawing a diagram. Okay, so we want to draw a diagram of the system of objects and label what we know. So first we want to draw the pulley. And there's the axis of rotation. So we'll call this the axis. We do know that there's going to be a distance vector r. Now we know that the mass of the pulley is going to be mp. We can assume that there's going to be some sort of acceleration, angular acceleration, towards the side where we're pulling. And we can also draw a string representing T1 from us pulling on the string. So I'll draw a hand, like this. On the other side of the pulley, there's a hanging mass. So we'll call this MH for the hanging mass. We also know that the hanging mass is going to have gravitational force acting on it, so mhg to be more precise. So it seems like we've got everything labeled that we should. The only thing missing is a coordinate system. So why don't we say up is positive, and that the counterclockwise direction is positive. So now let's write down what values we're given. We are given the mass of the pulley being 1.2 kilograms. We know the radius of the pulley is 0.075 meters. We know the hanging mass is 0.67 kilograms. We know that T1 is just the downward force that we're pulling the string with, which is 28 newtons. What else do we know? We know that G is equal to 9.8 meters per second squared. Next, we should probably look at some of the equations we can use for this. We do know that there are two Newton's second law equations we could use. We have F net equals to ma. In this case, the only one that could apply, that this equation could apply to, would be for the hanging mass, so we can change this to mha. We can also figure out the equation for net torque, which is I times alpha. And the key thing here is I is going to be equal to 1/2 mpr squared, because this is a solid disk. We also have our conversion equation for acceleration between the linear and the rotational world. So we have linear acceleration being equal to r times alpha. Okay, so now we have a whole list of known values and equations that we can use, plus a label diagram. We're trying to figure out the tension on the other side of the pulley, so we want to figure out T2. So that is our goal, because we've already figured out T1. So step 2, we want to find the net torque and apply Newton's second law. So in other words, we already know that T1 is equal to 28 newtons. So let's just underline that so we know that we've already figured out one of the answers. The next step is to look at the net torque acting on the pulley. So we do have the net torque being equal to I times alpha. In terms of the pulley itself, if we consider the counterclockwise rotation as positive, then we have a positive torque coming from T1, and we have a negative torque because it's acting in the counterclockwise, in the clockwise direction. So we have tau 1 minus tau 2, and that is equal to I times alpha. So we also know I is equal to 1/2 mpr squared, and alpha is simply equal to A over R. So another way to write tau 1 and tau 2, remember the equation for torque? Torque is equal to Rf sine theta, but in this case, both of these tensions are acting tangential, so that means if we have sine theta, in this case it's sine of 90 degrees, which is equal to 1. So we have RT1 minus RT2 is equal to 1/2 MP RA. We're able to factor out the R on this side. We can cancel out our R's. And we have T1 minus T2 is equal to 1/2 MPa. Okay, so in order to find this, T2, we need to rearrange. And we get T1 minus 1/2 MPa. We do have T1, we do have MP, we don't have A. So the next step, or as an aside, we want to find the expression for linear acceleration. So in this case, we do have to apply Newton's second law again with the hanging mass. So we have F net being equal to MHA. Technically, the mass is going to go up, so the acceleration is going to be going up, which means we have a positive acceleration. The net force acting on the hanging mass is going to be T2 in the positive direction minus mhg, which is equal to mha, and A is therefore equal to T2 minus mhg divided by mh. So all we have to do now, we have equation 1, we have equation 2, we need to let's just write this here. Sub 1 into 2. So now we have T2 equals to T1 minus 1/2 MP T2 minus mhg over mh. We want to solve for T2, so we have to put everything together, but this is so huge that we want to try and simplify it a little bit first. We have T2 equals to T1 minus 1/2 MP T2 over mh minus 1/2 MP negative mhg over mh. T2 is equal to T1 minus 1/2 MP T2 over mh plus 1/2 mpg. Okay, so now we want to move the term with T2 over to the left side. So we have T2 plus 1/2 MP T2. Just simplify this. MP T2 over 2 mh. That's equal to T1 plus 1/2 mpg. This is getting pretty big. We can factor out T2 and get 1 plus mp over 2 mh equals to T1 plus 1/2 mpg. T2 is then equal to T1 plus 1/2 mpg. divided by 1 plus mp over 2 mh. Okay, so all that's left is plugging in our values. T1 was equal to 28, and this is plus 1/2. Mass of the pulley was 1.2. Gravity was 9.8. We're going to divide by 1 plus the mass of the pulley, which is 1.2, over 2 times the hanging mass, which is 0.67. When you punch this into the calculator, you should get T2 equal to 17.87 newtons. So now you have T1 and T2, and you've finished the problem. So in this question, it's asking how much work must be done to accelerate a baton from rest to an angular speed of 7.4 radians per second about its center. Consider the baton to be a uniform rod of length 0.53 meters and mass 0.44 kilograms. So let's start with a plan. This is a rotational work problem. We don't need a diagram for this, but rather just a statement of givens and unknowns. We know that the baton is considered a uniform rod with mass and length, so we're going to need the correct equation for a moment of inertia. So let's start with step number 1. There will essentially just be one step. We want to use the work energy theorem and solve. So once we have our moment of inertia, which is I equals to 1 over 12 ml squared, we are also given its final and initial angular speeds. Maybe we can use the definition for rotational kinetic energy. So we know that work is equal to delta Ke, which is then equal to Kef minus Kei. We do know the initial and final angular speeds, so that means we are able to solve for delta Ke, and we can use the work energy theorem to solve for the work involved. So we have this. We can solve for work. It's 1/2 I omega F squared minus 1/2 I omega I squared. So what other given values do we have? It's accelerating a baton from rest to an angular speed of 7.4. So we know that omega I is equal to 0 and omega F is equal to 7.4. So that essentially means that this whole term on the right goes to 0. We have W being equal to 1/2 I omega F squared. W is equal to 1 over 2, 1 over 12 ml squared omega F squared. We do know that M is equal to 0.44 and L is equal to 0.53. So we already have everything we need to solve for this. This is 1 over 24 ml squared omega F squared. So W is equal to 1 over 24 times 0.44 times 0.53 squared times 7.4 squared. And that gives us 0.282 joules. So therefore, 0.282 joules of work is done to accelerate the baton. So now let's move on to angular momentum. In the linear world, we had linear momentum P equals mv. So in the linear world, we had P equals to mv. But in the rotational world, we have angular momentum. And by now, you're probably familiar with all of the rotational analogs of the linear world. So when we move on to the rotational world, we know that the rotational equivalent of mass is I, the moment of inertia, and the rotational equivalent of velocity is omega for angular velocity. So here we have the rotational world. We know we have I and omega, which means we should probably have an equation for angular momentum L. So we have angular momentum L is equal to, instead of m times v, we have I times omega. But as always, we need to be able to relate this back to the linear world, so we should probably come up with an equation so that we can directly relate angular momentum L to linear momentum P. So the following analysis will help us create an equation to connect the two together. So we already know that I is equal to kmr squared. So start this off with how can we connect linear to angular momentum directly. So we know that I is equal to k mr squared, where k is a factor that changes depending on the shape of the object and where its axis of rotation is. So for example, in the past, when we talked about a pulley, which is a solid disk, it would be I equals to 1/2 mr squared. And if you're talking about a hollow cylindrical shell or a hoop, you're looking at I equals mr squared. So just remember, different shapes have different moments of inertia. Another thing we know is that V is equal to R times omega. So omega is equal to V over R. So now we have two different ways of representing our I and our omega that have to do with the linear world, because M and R and V have to do with linear quantities. So we can rewrite our equation for angular momentum. And we get L is equal to I times omega equals to kmr squared times V over R. One of the R's cancels out, and we get kmrv. So what's special about this? The linear momentum is equal to P equals mv. So we have but linear momentum P is equal to mv. So can't we rewrite L as kr times mv? And in this case, our mv can be replaced by P. So now we have a direct relationship between linear momentum and angular momentum. But to make things a little bit easier, we don't always want to have a k in front of our expression. Let's look at an example of a point particle. So if we're looking at a point particle moving around a circle, we have a point particle, it moves around in a circle, and there's an axis of rotation. Essentially, the point particle is going to trace out a circular hoop, which means the moment of inertia is going to be mr squared. And that means our k is simply equal to 1. So that's going to make our equation for angular momentum that much easier. This means that L is equal to 1 rp, or just rp, for a point particle. Okay, so we have an equation for angular momentum. We were able to connect it to linear momentum, but it seems like we're missing something yet again. Remember, momentum is a vector, so that means it has a magnitude and a direction. Right now, we've only been looking at magnitudes, but what happens if your momentum vector p is not tangent to your circle? So just like our analysis with torque, we only care about the tangential component of momentum. So that means, remember with torque, we had defined it as Rf sine theta. Now we have to define our p, or our linear momentum, and only take the tangential component of that. So we want to now look at a generalized equation for angular momentum. So that means we would want the tangential component of the momentum vector, or p sine theta. So this means L is equal to rp sine theta, which is equal to rmv sine theta, which is also equal to r cross product with p. So now we have a generalized equation for angular momentum, and it's very important to know that this is for a point particle, because we've used L equals to RP. So just to recap, this equation only works for a point particle going around in a circle. Remember, the moment of inertia equation will change for different shapes, so be careful when you apply this equation to a uniform disk, like throwing a frisbee, because you would need to use I equals 1/2 mr squared for a solid disk. So now we can move on to another very important topic, the law of conservation of angular momentum. It's pretty much identical to the law of conservation of linear momentum, but instead of P, we have L. So we have Li is equal to Lf. But it isn't as easy as just changing letters. We need to understand where this comes from and whether there's any conditions involved. So when an ice skater goes into a spin and pulls their arms closer to their body, or when you go for a jump off a diving board and fold your body to do a flip, conservation of angular momentum is at work. Let's first see how we can measure the change in angular momentum over time. So if we wanted to figure out the change in angular momentum over time, we would want delta L over delta T. That means you'd want your final angular momentum minus your initial angular momentum divided by delta T. So what is our angular momentum defined as? It's I omega, so I omega F minus I omega I divided by delta T. Let's factor out the I, which means we have omega F minus omega I over delta T, which is simply I times delta omega over delta T. So what is delta omega over delta T? That's just angular acceleration. So delta L over delta T is simply equal to I times alpha. And what else is special about this that we've seen before? I times alpha is also equal to the net torque. So that means net torque is equal to delta L over delta T. So this is pretty cool. The net torque is equal to the change in angular momentum over a specific period of time. But what does this tell us about the law of conservation of angular momentum? It means if we want something to be conserved, that means its initial and final values shouldn't change. So we want to conserve angular momentum. So if we want to conserve angular momentum, delta L needs to be 0. The only possible way for this to happen is if your net external torque is 0. So if we want delta L to be equal to 0, then our net torque must also be equal to 0. So therefore, we come to the conclusion that angular momentum is conserved only if the net torque is 0. So let's write this down. Angular momentum is only conserved, so that's Li is equal to Lf, when the net torque is equal to 0. So now for the fun part of any momentum topic, collisions. In the real world, or in the rotational world, we have rotational collisions. So what is this exactly? This happens when you drop something, like a record that may or may not be spinning, onto something that is, like a turntable. Another example would be if you decide to run at and jump onto a small merry-go-round and cause it to rotate due to your impact. Since only internal forces are involved during this process, it follows that a system's angular momentum would be conserved, and we call this a rotational collision. So, rotational collisions involve objects that spin freely so that L, or angular momentum, is conserved. So we'll go through a few practice problems to help familiarize you with these types of problems as well. In this problem, you sit on a spinning stool and hold a dumbbell in each hand. At first, you hold the dumbbell with your arms outstretched and spin about the axis of the stool with an angular speed of 3.72 radians per second. The moment of inertia in this case is 5.33 kilogram meter squared. While spinning, you pull your arms to your chest, reducing the moment of inertia to 1.6 kilogram meter squared. what is your angular speed now? So in terms of this problem, this is a conservation of angular momentum question. It seems like we have to calculate our current angular speed using Li equals Lf. So we can go ahead and try that out. The reason why we went to conservation of angular momentum is because it gives us the moment of inertia in both cases, and there's angular speed in both cases. It's just we are missing one of the angular speeds that we have to find. So a diagram would not be as useful here unless the question specifically asks for it, which it doesn't. So let's start by writing out step 1. And there should just be one step. Should be state your known values, and apply the law of conservation of momentum. So what are we given? We are given omega I is equal to 3.72. We don't know omega F, and that's what we're trying to find. We are given the initial moment of inertia, which is 5.33, and we're given the final moment of inertia, which is 1.60. So with the conservation of momentum, we have Li is equal to Lf. II omega I is equal to IF omega F. We solve for omega F, which is II omega I divided by IF. And just plug in the numbers, 5.33. Omega I was 3.72 divided by 1.60. And we get the final angular momentum of 12.39 radians per second. And that is our answer. In this question, a disc-shaped merry-go-round of radius 2.63 meters and mass 1.55 kilograms rotates freely with an angular speed of 0.641 revolutions per second. A 59.4 kilogram person running tangential to the rim of the merry-go-round at 3.41 meters per second jumps onto its rim and holds on. Before jumping on the merry-go-round's rim, the person was moving in the same direction as the merry-go-round's rim. So that means it's tangential. What is the final angular speed of the merry-go-round? So we see that we have a disk with a radius of r and a mass of, let's call mm for the merry-go-round. This means that the moment of inertia for a solid disk would be I equals 1/2 mr squared. We also know that it has an angular speed of 0.641 revolutions per second, so that means we'll have to convert to radians per second at some point just to make sure the units work out. Now, the person runs at the edge of the merry-go-round at 3.41 meters per second and then jumps onto it. So this is essentially a rotational collision. We want to find the final angular speed of the merry-go-round, and that means we should be able to use conservation of angular momentum. So step 1, we do need to draw a diagram of the system and label what we know. So we want to draw a diagram and state our known values. Let's draw the merry-go-round. We know that there's an axis of rotation right at the middle, so we'll label this the axis. We also know that the mass of the merry-go-round, we'll just call that mm, and it has a moment of inertia I. It also has some sort of angular velocity of omega I, and we can label this as the initial condition. What else can we label? We know we have some sort of radius r, and also there is a person that's running at the merry-go-round and wanting to hop on at an initial speed of vi. So let's say the mass of the person is mp. So what values are we given? We know mm is equal to 155 kilograms. We know mp is equal to 59.4 kilograms. Omega I is 0.641 revolutions per second, but in one revolution there's 2 pi radians. So that means omega I is equal to 4.0275 radians per second. We also know the radius is equal to 2.63 meters, and we know that the moment of inertia is 1/2 the mass of the merry-go-round times r squared. Then we have our final scenario, where we still have the merry-go-round. We have an axis of rotation. The total mass is now m plus mp, and we'll get to this later. There's also a final angular speed, or velocity. So we don't know what the final angular speed is, and that's what we want to find. We also want to note that when we're looking at this, mm and mp still have to be separate. In linear collisions, we were able to combine the two masses together, but in this case, the two different masses going around in a circle are going to have different moments of inertia, and because of that, we have to do our analysis separately. So the next step, where do we go from here? We might as well start applying the conservation of momentum and solve for the unknown value. So we've drawn our diagram. We can say that angular momentum is conserved because the merry-go-round rotates freely. Let's now set up our equation, but keep in mind there are two objects here, the solid disk and the person. Initially, we have to consider their momentum separately, and then at the end they're stuck together. Initially, the angular momentum of the disk can be in angular terms. So here, let's just write down Li is equal to Lf. And that means the total angular momentum initially and the total angular momentum in the final stage. We have two objects, so that means we must consider the initial angular momentum of the merry-go-round and the initial angular momentum of the person. We'll leave the final angular momentum for later, and we'll look at just the initial part now. The angular momentum of the person, we don't have angular values for this, but rather linear, so we have to use the linear definition of angular momentum, which is L equals RmV sine theta. So let's backtrack. For Lmi, we know that it's the merry-go-round, it's a solid disk, and it does have angular momentum, so we can use I So the moment of inertia of the merry-go-round times the initial angular speed of the merry-go-round. Plus, now we're looking at the person, and the person is moving linearly tangential to the circular path of the merry-go-round. So we use RmV sine theta. So this is R, mass of the person, times V sine theta. But keep in mind, sine theta is simply sine of 90 degrees because the velocity vector is tangential to the radius of the disk, and we have a right angle over here, so we have Im omega I plus RMPV. So what else can we substitute for this? We know that the moment of inertia is 1/2 mr squared. So we can replace this with 1/2 mmr squared omega I plus r mpv. Okay, so now it's probably time to look at the right side of the equation. We need to know the final angular momentum of both objects. So we need the final angular momentum of the merry-go-round and also the final angular momentum of the person. When we're looking at the final scenario, both masses are now rotating at the same angular speed, so they both share omega f. There's no longer any linear component to this, so both of these are going to be Im omega f, and you have the moment of inertia of the person times omega f. And now the question is, how can we represent the moment of inertia for both of these objects? We already know we can represent Im as 1/2 mr squared, but for the person, the person is like a point object going around the circle. So we're going to use I is equal to mr squared. So this is going to be mp r squared omega f. This means we can replace Im with 1/2 r squared omega f plus mp r squared omega f. Okay, so all we have left to do is just to solve for omega f. So we should probably factor it out on the right side. We do have 1/2 mmr squared omega I plus rmpv equals 2. We can factor out r squared and omega f to get 1/2 mm plus mp, which means omega f is equal to, let's factor out an r on the left side. We have 1/2 mm r omega I plus mpv divided by r squared 1/2 mm plus mp. That gives us 1/2 mmr omega I plus mpv divided by r 1/2 mm plus mp. So this is getting pretty long. It's time to plug in our numbers and solve. We have 1/2 times 155 times 2.63 times 4.0275 plus 59.4 times 3.41 divided by 2.63 1/2 times 155 plus 59.4. When you punch all of that into the calculator, you get 2.844 radians per second as your final angular velocity of the merry-go-round and the person. The last topic we want to look at is static equilibrium. When you're trying to balance an extended object, like a rod, of course you want it to be balanced translationally or linearly so that it doesn't fall to one side. But there's also an option for that object to rotate, right? Especially if it's suspended. This means that you also need to balance the object rotationally so that an extended object, when suspended, doesn't rotate or become lopsided. Because of this, static equilibrium is only achieved by an extended object if it meets both of the following conditions. So we should write down that static equilibrium is when an extended object is balanced translationally and rotationally. So it must meet the following two conditions. Number one, the net force acting on the object must be 0. So that means the sum of the horizontal forces must be 0, and the sum of the vertical forces acting on the object must be 0. Next, we have to look at the rotational world, so the net torque acting on the object must be 0. So in this case, we have the sum of all torques being equal to 0. Remember that these two conditions are independent of each other, so for any question related to static equilibrium, we must do a full analysis on the net force and the net torque acting on the object. And as with all equilibrium and balance topics, we must also approach the topic of center of mass. Before, we only looked at an individual object or a system of objects as one and located the center of mass using our XCM and YCM equations. But now that we know about static equilibrium, we can tackle problems where we don't just worry about the center of mass of a system of objects, but also zero torque. In order for a system to be fully balanced, it must be in static equilibrium, and therefore, if you're handling a rod, let's say, then you must suspend the rod using a string tied at exactly its center of mass, or else the system will experience a torque. So, in order to fully balance an extended object that is suspended, it must experience zero torque and be suspended at its center of mass. So that means, for example, if you're trying to hang a rod, like this, maybe you have a heavier object here and a lighter object here. You're going to have to find the center of mass of this object, which might be over here. We'll call this XCM for the center of mass. And that is where you would suspend your rod so that a zero torque is experienced by the system so it does not rotate. Now let's go through a few practice problems related to static equilibrium. Let's go through a practice problem. So, a 5-meter long diving board of negligible mass is supported by 2 pillars. One pillar is at the very left end of the diving board, and the other is 1.5 meters away from this pillar. Find the forces exerted by the pillars when a 90-kilogram diver stands at the far end of the board. So let's first make a plan. This is a very different type of question than the ones we've done before. It has everything to do with forces, so it seems like we'll have to first draw a diagram in order to make sense of the objects in the system, and also what types of forces are acting on each. After that, we must recognize that this is a static equilibrium question. In order for the diver to stand at the edge of the diving board, the board obviously can't move or rotate. So we can assume that the system has to be in static equilibrium and solve for our unknown values. So step number 1, we do need to draw a diagram and state our known values. So it seems like there's a diving board. So we'll draw that first in green. There's the diving board. There is a pillar on the left side, which we'll call pillar 1. And the other is 1.5 meters away from this pillar. So let's also draw some sort of ground. And there's going to be a second pillar here, which we'll call pillar 2. We know that the distance between these 2 pillars, let's call this D. Let's also label this as the dive board. There is a diver. We'll just draw a rectangle for the diver. Has a mass of m. And it is at the very far end of the board. So that means the total distance of the board is L, and that's how far the diver is away from the left side. Let's see what other things we should label. This is going to be a question that's related to static equilibrium. We're going to have to look at forces and torques. So if the diver was standing on the right side, it would mean that the board's axis of rotation might be over here on the far left, so we're going to call this the axis. We should look at what forces are acting where. We do know that the diver is going to experience force of gravity going down, so we have mg going down. We also have 2 unknown forces exerted by the pillars. So let's just draw these forces going up for now. Once we do the calculations, we should be able to determine whether they are positive or negative. So we have F1 and F2. Now it doesn't seem like we need anything else, so let's just write down what we're given. We're given L is equal to 5.00 meters, D is equal to 1.50 meters, M is equal to 90 kilograms, and G is equal to 9.8 meters per second squared. Let's say up is positive and the counterclockwise rotation is positive. So we have our diagram. The next thing we should do is really just analyze the forces linearly and rotationally. So let's start with linear because that's easier. So we have this general statement and instruction for this step to analyze the linear forces in each direction. In this case, we don't have any forces acting left or right or in the horizontal direction, so we just have to care about the vertical direction. So with our diagram, we can see that the diver exerts a force of mg, a distance L away from the axis of rotation, and this points downwards. We also have two forces exerted by the pillars, which we'll label as up for now. There are only vertical forces here, so we're going to look at the y direction only to make sure it balances out. So we have this. We drew F1 and F2 as positive, so F1 and F2 are in the positive direction. And we have minus mg, and they should be equal to 0. We'll call this equation 1. That's pretty much it for analyzing our linear forces. Step number 3, we need to analyze torque. So step number 3, let's analyze the torque. We do know that the net torque is also going to have to be 0 for static equilibrium. So we have the total sum of our torque. If our positive rotation is counterclockwise, then technically F1 and F2 are in the positive direction because it's going to be a force applied this way around the axis. So that means the torque will be positive for both of these, and we have R1 F1 sine theta plus R2 F2 sine theta minus mg is now going this way, so that means we have minus Rm for the length that the diver is away from the axis of rotation times mg sine theta. That should equal to 0. So is there a way to simplify this? We know that R1 is equal to 0 because the distance that pillar 1 is away from the axis of rotation is just 0 meters. R2 is simply D, which is 1.5 meters, and Rm is simply L, which is 5.00 meters. So that means I can remove R1 because it's just 0, and Rm is just L. So let's simplify this. We have 0 plus R2, which is D, F2. We know that the forces are tangential to the circular path, so that means it's sine of 90, which is just 1, minus L mg F1 equals to 0. We can then solve for F2. F2 is equal to LmG over D. And let's call this equation 2. The last step is really just to solve for the question. We have two equations. We have an expression for F2. We can plug it in to equation 1. So sub 2 into 1 and solve for F1. So we have F1 plus LmG over D minus mg is equal to 0. We have F1 is equal to mg minus LmG over D, which is equal to mg 1 minus L over D. F1 is equal to 90 times 9.8 times 1 minus 5.00 over 1.50, and F1 is equal to minus 2058 newtons. So we can see here that the force is going to be pointing in the opposite direction. Now we know that F2 is equal to LmG over D, which is simply 5.00. The mass is 90 times 9.8 divided by 1.50. F2 is equal to 2940 newtons, which is a positive value. So we can now see that the force exerted by the first pillar is 2058 newtons down, and the force exerted by the second pillar is 2940 newtons up. But why? Imagine removing the first pillar on the left. So if we remove the first pillar on the left, this would mean that the force from the diver on the right would make the board rotate around the second pillar. That means you would need another downwards force on the other side to hold the board in place. So it does make sense because it has to balance out. So in this question, a 0.122 kilogram remote control that's 23 centimeters long rests on the table with a part of it, length L, overhanging the edge of the table. It is this overhanging part that has the power button. To operate the power button on this remote requires a force of 0.365 newtons. How far can the remote control extend beyond the edge of the table and still not tip over when you press the power button? So this is a question about how far the remote control can hang over the table and also let you press the power button to play. Assume the mass of the remote is distributed uniformly and that the power button is 1.41 centimeters from the overhanging end of the remote. So this is another static equilibrium problem, but more complicated. We have a remote whose mass is distributed uniformly. This means that we might want to think about the center of mass, xcm, and it should be right in the center of the length of the remote. We're also trying to find the maximum overhang L, which means we would need to look at a case where the torque about the table's edge caused by the button force is balanced by a torque caused by the weight of the remote. So the weight of the remote is going to act exactly at the center of mass of the remote control. But first let's draw a diagram because there's so many components. So we have our table. And we're also going to have our remote control. So the center of mass of the remote control probably be right here in the center. I'm drawing it a little bit off so that I can have some room to label things. So we call this XCM. We also have an axis of rotation. If we were to push a button, then the remote would rotate about this axis. Let's also say the remote button is right here. So this red button, it is a distance B from the edge of the remote. We also know that the remote must have an overhang of L. And this also means that we need to consider the value of XCM and where that is in relation to L and B. The total length of the remote is 0.23 meters because it's 23 centimeters. And what else can we label? Should probably label some forces. So we'll move to green for the forces. At the center of mass, you have the force of gravity acting on the remote control, which is mg. You also have the force of the push on the button. So it's going to come down from the top, and you have a force. So let's consider the counterclockwise rotation is positive, and let's also consider what we're given. So we know F is equal to 0.365 newtons. We know M is equal to 0.122 kilograms. XCM is equal to 0.23 meters divided by 2, because the center of mass is just half of the total length. You have G being equal to 9.8 meters per second squared, and the button being 1.41 centimeters or 0.0141 meters away from the far edge. And we are trying to find L. So step number 2, we want to analyze the torque. When we press the button at that maximum overhang L, we want the torque to be in equilibrium. This means that the net torque must be equal to 0. And that means we need to figure out what kind of forces are acting where. So in this counterclockwise direction, we know that it's around the axis of rotation. On the right side, with F, it's opposing the motion which means that it's going to be a negative torque. But over here, where mg is, it is along and tangential to the rotational motion, so it's positive. So therefore, we have RR mg sine theta minus RB F sine theta being equal to 0. RR is simply the distance of the remote control away from not the remote control, it's the distance that the mg force is acting away from the axis, and RB is the distance that the applied force is acting away from the axis. So, we know that the distance that mg acts away from the axis is xcm minus L, because this is also xcm, and we're looking for this distance right here. Now, for RB, that's the distance the remote control button is away from the axis. It is simply going to be L minus B. Okay, so now we put all of that together. We have RR mg sine theta minus RBF sine theta equals to 0. One important thing to note is when we're looking at the axis of rotation and we're looking this way as positive, we have our force going down this way, and we have our mg going this way. And in this case, they're all at right angles to the axis. So that means we have sine of 90 degrees being equal to 1. That means RR mg minus RB F is equal to 0. Let's replace these with our new definitions. xcm minus L mg minus L minus BF equals to 0. We want to solve for L. So that means we must expand and collect like terms. xcm mg minus L mg minus LF plus BF is equal to 0. We have xcm mg plus BF is equal to L mg plus LF. And we can factor the L out to get mg plus F. Now we have L is equal to xcm mg plus BF divided by mg plus F. And all we have to do is just plug in our known values. We have 0.23 divided by 2. M is 0.122. Gravity is 9.8 plus B, which is 0.0141. F is 0.365 divided by M, 0.122 times 9.8 plus the force 0.365. So once you punch that into a calculator, you get L is equal to 0.0914 meters, which is equal to 9.14 centimeters. So if you want to be able to push the power button on your remote control of length 0.23 meters, then you would have to push it within an overhang of 9.14 centimeters.